This is a brief lecture on how latitude and longitude were determined prior to the invention of global positioning systems. Global positioning systems were developed by the United States government, the Department of Defense, in the 1970s and became public during the Reagan era in the mid 1980s and progressively increased in technology and advancements. And now we are to where we are today, and well into the 21st century, and global positioning systems have an accuracy of less than a meter in many cases. And in the United States, if you have a cell phone, you have access to global positioning technology, whether you have it activated or not. It really is something that we probably take for granted, considering uh, considering what our ancestors had to use in the past, using celestial bodies and other methods of determining their position on the spherical face of the Earth. Prior to global positioning systems, they would have to have an almanac of celestial bodies prepared by astronomers. They'd have to have accurate charts prepared by cartographers. The navigators would need a quick and easy mathematical method for reducing the data from their celestial observations to a position on a chart. The charts I'm meaning by maps. They also had something in the 18th century that was developed, something called a chronometer that gave them a more precise method of determining longitude, which proved to be much more difficult. But first, let's look at latitude. Latitude is much easier, and it was used. It was determined using the Polaris star, the North Star, which is situated directly north of our polar axis in the North Pole. So anywhere above the equator in the northern hemisphere, the Polaris star could be used to determine their latitudinal position. In the southern hemisphere, it's a little bit more complicated, but there were star positions that they could use, the Southern Cross being one of them. It's a very famous, well-known constellation in the southern hemisphere that mariners could use to determine their latitudinal position in the southern hemisphere. But in this little lecture, we're just going to talk about the northern hemisphere because it's where we live, and it's a very simple concept. If you look at this image, the star, North Star, is directly in the middle, and we have star trails as these stars move their position in the night sky. The North Star does not, and this is how this was determined many years ago. We have our horizontal plane. So if you're standing on the surface of the Earth, in Boulder, Colorado in this example, which is 40 degrees north of the equator, the Earth is on a curved surface, so we'll just kind of hypothesize that we're standing on this curved surface, but we're on a horizontal plane, and we're going to use this plane to compare it to our direct line of sight to the North Star. So we have this angular measurement. This is 40 degrees north. If we were standing at the North Pole, we'd have to look directly overhead and we'd find the North Star. This gives us our 90-degree angle, 90 degrees north latitude. If we're standing at the equator, the North Star is just below the horizon. We can't see it, so there's no angular measurement for us to measure. So it's 0 degrees. Excuse me. If we were to go out in Duluth and observe these celestial observations, my apologies, I'm still getting over a cold. You'll find that your position is 46 degrees, 48 minutes, 6 seconds. My apologies, I had to get over my coughing fit here, so hopefully I can make it through the next few slides without coughing. In the 16th century, the sextant was developed, and this just provided an instrument to compare these celestial bodies with the horizontal plane. So what they would do is they would put the celestial body into their sights, the sun in this example. Using a level, they would make sure that their horizontal plane that they were level with the surface in which they were standing. there would be a scale that they could read. So as this bar slid, depending on where that celestial body is located and how you had to adjust the instrument to make these measurements, it would tell you then what angle that you're measuring. So if you've ever seen the movie Master and Commander, which probably most people have, they demonstrated this in that movie, and you'll see this instrument demonstrated in other historical films as well. Here's a man demonstrating this. He has his horizontal plane established here, and he's adjusted the arm of his instrument to bring the Polaris star into his sights, and then using the arm below, he could then read the angular measurement. This is just an example from your book. I just wanted to throw this in here as you're reading through those materials. Here's an example of reading that angular measurement from the center of the Earth, but obviously we don't have the instrumentation to do that, especially not a few centuries ago. But we have a horizontal plane, and the sight's in with the North Star, giving us a 50-degree location on the surface. Now, longitude is a much more difficult angular measurement. They couldn't use celestial bodies for this, and so it was caused a lot of problems. A lot of lives were probably lost due to the inability to measure longitude. Coastlines were misplaced on a chart. A lot of things were mismapped. Not probably, they were. And a lot of that had to do with their inability to accurately measure longitude. But the concept of it is really quite simple. The Earth is 360 degrees around. It rotates every 24 hours. So if we divide 360 by 24, we end up with the number 15. So that number tells us that the Earth rotates 15 degrees for every hour. So Boulder, Colorado, again here, comparing it to London, which really this should say Greenwich, England, but they're in the same time zone, so that's okay. Boulder is 7 hours behind Greenwich, England. So if we take that knowledge of 7-hour difference and multiply it by 15 degrees, we'll find that Boulder is 105 degrees west of the prime meridian. Now, the chronometer was developed by a man named John Harrison in 1762. He was an Englishman. He was an inventor. The monarch put out a competition to all the inventors to develop some type of mechanism to measure longitude. It was a 20,000-pound prize, and John Harrison developed this mechanism. And really all it is a clock. It's a clock that can keep accurate time for long periods of time. Kind of similar to the atomic clock, which is what our global positioning satellite systems use, because time is of the essence with global positioning systems. Now, obviously, this is not an atomic clock. It can't hold time as accurately, but for the day, this clock was as good as it gets. So what the sailor would use, they'd use a sextant to determine local high noon, because in order to compare your local time of where you're at with the time on the chronometer, you'd have to know what your local time is. You compare that time to the chronometer's time, because before you left the port, before you left England, or wherever you were leaving from, you set that clock time to Greenwich Mean Time, because you're always going to use Greenwich Mean Time to determine your longitudinal position. So you take that hour difference, multiply it by 15, because there's 15 degrees in 1 hour, to determine what longitudinal position that you're actually at. So let's just look at an example here. Here, these sailors have left Europe and they traveled west, and now they're somewhere over here by Nova Scotia and Newfoundland here. They need to determine what is our longitudinal position. So they determine high noon with a sextant. So what is their local time? They compare that with a chronometer. So they look at the chronometer and they say, oh, it's 4 p.m. in England at Greenwich, England right now. There's a 4-hour difference. So we take that 4 hours, multiply it by 15. That equals 60. 15 degrees in 1 hour tells us that we are 60 degrees west of Greenwich Mean Time. So this was the logic behind determining longitudinal positions prior to advancements in technology.